skill discovery for planning and exploration using deep skill graphs. The study of hierarchical reinforcement learning is considered with learning skills, which are modular, closed-loop control policies. Thanks to sudden precompensing, we can mathematically model these skills using the options framework. Each option is defined using an initiation set, which is the set of states from which option execution is allowed to begin. The termination condition, which describes the set of states in which option execution is deemed successful. And finally, an option policy, which is a closed-loop controller that drives the agent from states in its initiation set to those in its termination set. While a multitude of papers have studied the problem of how such options can be discovered autonomously, we build on our previous work of deep skill chaining, which recursively learns options backwards from the goal state to the start states of the MDP. Here is an example of how deep skill chaining learns and refines initiation sets of options in a continuous version of the four rooms domain. Note that the termination condition of the option visualized in the right subfigure is the initiation condition of the option shown in the left subfigure, which in turn drives the agent to the overall goal of the MDP. We believe that the nature of the problem that an RL agent is confronted with directly informs the way learned skills should be organized. When the agent has a single start state and a single goal state, the appropriate data structure in which skills are arranged is a skill chain. When the agent has multiple start states but a single target goal state, it must organize learned skills in the form of a tree rooted in that goal state. Both of these situations were covered by the skill chaining algorithm. However, if the agent can start anywhere and can be asked to go anywhere in the state space, it must learn to organize skills in the form of a graph. Organizing skills in this way allows the agent to leverage planning to solve problems by compositionally combining discovered skills. Another shortcoming of the skill training algorithm was that discovered skills were tied to the MDP's reward function, limiting applicability to the LifelongRL setting. The deep skill graph algorithm, on the other hand, takes up the challenge of learning task-agnostic skills in the absence of such extrinsic rewards, and in doing so, learns skills that can be used to reach novel goals at test time in a few-shot manner. Skill graph construction iteratively proceeds in 3 steps. In the first step, the DSG agent discovers a target or salient event it would like to reach. Since the target state here lies outside the graph, the agent does not yet have the necessary skills to reach it using planning. In the second step, the agent identifies the node in the graph closer to the target state identified in step 1. It then constructs a plan, shown here with red arrows, inside the graph to reach this identified node, which is shown in green here. Once it reaches the green node, it uses deep skill chaining to construct a series of skills that eventually connect the target state to the existing portion of the graph. Now the salient event from step 1 is just another node in the graph that can be easily reached using its planning-based control loop. This process repeats when a new salient event is generated until the skill graph has covered ever-increasing portions of the state space. To demonstrate the properties of deep skill graphs, we consider 3 maze navigation tasks in Mojoko. In all our experiments, the agent is not provided with any extrinsic rewards during training, where it discovers its own goals, and in doing so, constructs a skill graph. At test time, it plans using its acquired graph to reach novel goals in a few-shot manner. A consequence of our graph construction procedure is the agent's exploratory behavior, which we demonstrate here in the ant maze domain. We compare the states visited by the DSG agent and those visited under a random walk. We find that acquiring and using skill graphs can lead to temporarily extended exploration, as opposed to the dithering behavior of random walks. even in the absence of an extrinsic reward function. These figures provide some intuition on why deep skill graphs can effectively explore large regions of the state space. The skill graph begins at the start state and incrementally expands into large unexplored regions. By planning and executing learned skills inside the graph, the agent can reliably get back to its frontier, which is represented by the outermost vertices of the graph. Exploration from the frontier in turn allows it to amass experiences it needs to further expand the graph. Similar properties of incremental graph expansion can be seen with the point agent acting in a large complicated maze. By interleaving planning and chaining in this way, the DSG agent incrementally achieves mastery of ever-increasing proportions of the state space. To quantitatively evaluate our algorithm, we measure its success rate, which is the fraction of times it was able to successfully reach a randomly drawn goal in the given episodic budget. The blue and orange curves correspond to two variations of our algorithm. The green curve corresponds to the performance of goal-conditioned RL or UVFAs, and the red curve corresponds to deep covering options, another algorithm that can discover task-agnostic options. Our results suggest that in a moderate-sized point maze, a large point maze, and in ant maze, deep skill graphs can comfortably outperform baseline RL algorithms. In conclusion, we introduced a practical algorithm that compresses a large continuous MDP into a small abstract representation, which is suitable for planning. Our algorithm is task agnostic and can thus be used in the multitask or lifelong learning setting. Discovered skill graphs expand incrementally outward from the start state to large unexplored regions of the state space. Our results suggest promising exploratory behavior and few-shot generalization capabilities during test time. Thank you.